All right. Hello, everybody. I'm Valentin. I'm a postdoc at AI2 and UW. I'm very excited to be here, and I'm going to talk today about some work that we did on fluid language model benchmarking. I want to start by taking a quick look at the current state of LLM benchmarking. I think we are all aware that there has been a massive proliferation of benchmarks over the last few years. Benchmarks are now central to almost any point in the LLM ecosystem. They are being used for model development, for model leaderboarding, and even for model marketing. But at the same time, there's quite a few challenges that we face in LLM benchmarking, and I want to quickly highlight two of those challenges. So one, there's the problem of label noise or label errors in common benchmarks. There have been quite a few studies showing that even in the most popular benchmarks like MMLU, a substantial proportion of the items is actually mislabeled, which is a problem because we of course want to trust the results that we measure on the benchmarks. A second problem that I want to quickly highlight here is the problem of inefficiency. So it can be incredibly costly to run just one evaluation run on a benchmark. And for example, in the example here, which is based on Helm, it costs the authors more than $10,000 sometimes to just evaluate a single model, which is a bottleneck in practice, especially if we want to evaluate repeatedly, as for example in pre-training settings. Now, it's interesting to observe that some of the issues that we are facing in LLM benchmarking today are actually quite similar to problems that existed in standardized testing of humans roughly 40 years ago. And the solution that was developed back then by psychometricians was computerized adaptive testing. So the idea that rather than having one test which you give to any test taker, you adapt the questions in your test to the capability level of an individual test taker. So say you have a worse test taker, the worst test taker would get increasingly easy questions during the test, and better test takers would get increasingly more difficult questions over the course of the test. And there has been some research showing that this indeed leads to a higher efficiency of evaluation, and it also gives you a better quality control because there are certain ways of avoiding problematic questions, for example, mislabeled questions, as you do this adaptive testing. And these advantages are one of the reasons why most standardized tests that you can take in the US, for example, today, like GMAT, GRE, and SAT, they are all based on computerized adaptive testing. So the question that we were wondering about in this paper is, can we use a similar method to computerized adaptive testing? So can we adapt evaluation to a language model's capability level and in that way improve some of the issues that we are facing in LLM benchmarking today? And we make three contributions here. We adopt IRT, so item response theory from education, to measure characteristics of benchmark items, for example, their difficulty. We then introduce fluid benchmarking, which uses those characteristics, for example, the difficulty of benchmark items, to dynamically adapt the items that we give to a model to the model's capability level. And then we conduct a series of experiments in which we show that fluid benchmarking indeed results in a higher validity, a lower variance, and an increased efficiency of evaluation. So let's start by taking a quick look at IRT. So the basic functioning of IRT is as follows. We have a benchmark, which is just a set of items, so the items here are questions, and we create a population of models, so several LLMs, which we evaluate on all the items in our benchmark. And what we then can do is we can analyze the item-level response patterns of the population of models to learn interesting characteristics of the benchmark items. For example, we can see that items that were answered correctly by all the LLMs in our population are probably on average easier than items that were not answered correctly by any model in our population, right? So we can learn something about the difficulty of benchmark items. And there are different concrete IRT models out there. The model that we use here is the so-called 2PL model, so a two-parameter logistic model, where we try to model the probability that a certain language model answers an item correctly as a simple logistic function. And so here, A is the discrimination of an item, which indicates how sharply an item distinguishes between better and worse models. B here is the difficulty of an item, which indicates the ability level that an LLM needs to get a 50% chance of getting this item correct. And then theta here is the ability of a language model. Now you might wonder, why is this useful. So the key idea here is that we can use the estimated ability of a language model instead of accuracy. And to give you an example of how this looks like in practice, here is a toy benchmark consisting of 2 items. So we have item 1, which has a very high discrimination, A is 10, and we have item 2, which has an incredibly low discrimination of 0.1. So item 2 might be mislabeled or is an otherwise problematic item. And we say we evaluate 2 LLMs on this benchmark. This is the result of the first language model. The first language model gets item 1 correct and item 2 incorrect. So the accuracy is obviously 50%. But if we take the IRT approach, we would try to find the ability that maximizes the likelihood of this response pattern. And in this example, this ability is 0.5. Now we have also a second LLM. The second LLM gets the first item incorrect and the second item correct. So the accuracy is again 50%, but if we again take the IRT approach, we will try to find the ability that maximizes the likelihood of this response pattern, and in this example, the ability that does so is actually minus 0.5. So you can see that IRT, or ability estimation, is different from computing accuracy in the sense that it takes item-level characteristics into account, and this can be useful in many practical settings. And we are not the first to observe this. There has been quite a few studies already doing IRT-based methods in NLP and language model evaluation. But the key thing about all those studies is that they are still static. So they use IRT to, for example, come up with a better subset of items. But in the end, they do static evaluation. So this subset that they come up with is not adapted to the language model capability. So how can we actually do this? How can we adapt the items that we evaluate on to a language model capability level? So this is how fluid benchmarking functions. We have an LLM, and we start by evaluating the LLM on just one item. So we pick one item from our benchmark. We evaluate the LLM on that one item. So it's either correct or incorrect. And based on this model response, we then conduct the first ability estimation. And then based on this estimated ability, we select the next item. We again evaluate the model on that one item. We update our ability estimate, and then we pick the next item based on the updated ability estimate. So of course the question is, how do we actually do the item selection here? And what we use is Fisher information. So you can see that we have this A squared term. So items with a high discrimination are generally preferred. And you can also see that items whose difficulty is close to the current ability estimate are also preferred. So if you have a weak LLM, the ability estimation is gonna converge to some sort of low ability, and hence the items that are gonna be selected are also gonna be increasingly easy in that example. So let's take a look at our experiments. We focus here on evaluation during pre-training, which is a nice setting because model capabilities evolve rapidly, and hence having this adaptability seems to be beneficial. We evaluate six open LLMs where also all the checkpoints are available, and we benchmark each of those checkpoints on those 6 benchmarks that you can see here. For the IRT model that is underlying fluid benchmarking, we use the OpenLLM leaderboard, so we download model results from the OpenLLM leaderboard and train the IRT model on that. And in the paper, we look at various baselines. Here, I'm just gonna compare against the baseline, which I think is most commonly used, which is just computing a standard accuracy. First, a sanity check. Does fluid benchmarking indeed adapt to the capability level of a language model? To check this, we looked at the pre-training of Olmo 1. So here on the x-axis, you can see the checkpoints of Olmo 1. And on the y-axis, you can see the items of HellaSwag ordered by their difficulty. So the most difficult items here at the very top, and the easiest items are at the very bottom. For the first checkpoint, we start with an item of average difficulty. And notice this is almost a randomly initialized model. So the model can't really solve this. So it gets the first item correct. The next item is gonna be easier. The model gets this incorrect again. So the next item is gonna be easier again. And so you can see that we move down and down and down in difficulty until we reach the range of the easiest items in our benchmark. Now, as we train the model, we observe that fluid benchmarking automatically focuses more and more on the more difficult regions in our benchmark. So it does what we wanted it to do. It is indeed adapting to the language model capability. Now, what are the effects of this on evaluation quality? Of course, we want to see some sort of downstream advantage of doing this. And in the paper, we look at different dimensions of evaluation quality. Here, I'm just going to focus on validity, variance, and efficiency. For validity, we evaluate to what extent the estimated performance on one benchmark generalizes to the performance on other benchmarks that measure the same capability. So for example, different common sense reasoning benchmarks. And we compute the distance in the ranks between those benchmarks. So lower ranked distances are generally better here. On the left-hand side, you see standard accuracy. And you can see that there's quite a bit of fluctuation in the ranked distances, but overall, and sometimes they are quite large, so we're pretty far off from the true rank of the model. For fluid benchmarking, overall, the ranked distances are much lower, and we are also consistently much better than for standard evaluation. I don't have a lot of time to go into this, but we actually find in the paper that one reason for this increased validity is that we drastically decrease the number of mislabeled items that we evaluate on by almost 99%. So we really get this advantage of adaptivity by avoiding mislabeled items. In terms of variance, we analyze how smooth the training curves are that we get, and we find that the training curves for fluid benchmarking are substantially smoother than for standard evaluation, so we get a better signal of training progress. And finally, for efficiency, we find that these advantages of fluid benchmarking are particularly pronounced for small sample sizes. So here again, the results for standard evaluation for different numbers of items, and you can see that for fluid benchmarking, we are always better, but particularly for small sample sizes. So with 50 items and fluid benchmarking, we already get better results than standard evaluation for 500 items. So we really improve with small sample sizes. We are very excited about this, and we see a lot of potential for future work in this direction. And I want to briefly highlight 3 avenues that I think are particularly interesting. So for one, I think we need to develop a much better theoretical understanding of what are the best practices and what are the limitations of doing IRT-based evaluations in the context of LLMs. A lot of people are just using simple heuristics, and I think we need a more principled understanding. Then I think there's a lot of extensions, very straightforward, that we can do to fluid benchmarking, like looking at multimodal models, doing multi-stage testing, dynamic stopping. I think there's a lot in the psychometric toolbox that we can use to really improve LLM evaluation. And then finally, I think that adaptive item selection is not only interesting for evaluation, but could also be really interesting in the context of training. Okay, thank you, and I'm happy to take any questions.
Very nice talk, thank you. One question. So in your example, you had many of the models already evaluated on one of the benchmarks to determine the difficulty of each question. If we now start with a new benchmark where we don't have these results yet,
that's a great question.
What can you tell about that?
Yeah, so if you have a new benchmark, you would always need to calibrate, like in psychometrics, it's called calibrating. So you would need to train an IRT model on the benchmark. So you would need to evaluate a couple of LLMs, maybe 100 LLMs on this benchmark to learn those item properties, difficulty and discrimination, and only then could you use IRT or fluid benchmarking for this benchmark. So that's always the first step that you need to do. There are methods to evaluate, like train the IRT model with a smaller number of models, but yeah, like for a certain, you need to evaluate at least a small number of models on the benchmark first.
Thanks.
Hello, really nice talk. On the last point in the future work, that's what I was thinking about when you were talking about it, because I really like the adaptive compute type of network because they can kind of figure out if an item is hard or not, and there's all this literature about training on what actually is useful. How would that whole system work in adaptive LM training here? How would you I know we don't have 30 minutes to go about this, but just roughly how will we work on that?
Yeah, I think there are different ways that you could try out. I mean, there are certain theories about how items should be ordered by their difficulty in training, like in curriculum learning. So you could use IRT for that. there are also, I think, more sophisticated ways that you can try. So there are certain theories about how, like about the probability that a model should have to get a certain item correct, such that that item is useful if you use it for training. And with IRT, you can always, if you have an underlying IRT model, you can always estimate the probability that the model gets a certain item correct. Right. So you could, in a very, very targeted manner, in a tailored manner almost, pick items for training as well.
Right. Because also, like, I think a lot of compute is wasted in some shape or form.
Absolutely.
On, like, absolutely easy elements.
Absolutely.
Okay, thank you.